Hi folks, Mr. Long here. I'm just going to do a screencast on linearizing data. Okay, so this is how you linearize data to come up with an equation. Okay, and this works for exponential data that's in the form of y equals a times b to the x, or what we call a power function data, which is a times x to the n. So if this was ax squared, then it would be a very simple parabola, but n actually can be anything. N can be a decimal, in which case it's a root function, like a 0.5 would be the square root function, etc. It can be a negative function, so if it was -1, it would be a reciprocal function, right? So there's a variety of different forms that this takes up, the power function. Okay, so we're going to start with this set of data right here, and we want to come up with the equation using this linearization. And so I'm in a Google Sheet right now, and you have access to that through your school account, right? And it's probably a good idea to learn how to do this. It's using spreadsheets is very, very important as you go forward in your education. So this is our raw data. Now you can see this starts at 50, and then each time x increases by 1, it multiplies by 3. So 50 times 3 is 150 times 3 again is 450. So basically what it means is start at 50, multiply by 3 repeatedly. Okay, 50 times 3 to the x. So this is a nice clean set of data. You're not going to have that on your assignment or work that you do, or if you're writing up a lab next year in a biology course or something like that. You're going to have experimental data. You might not have your x values every increments of 1, so it won't be easy to see. So we already know the answer before we go through this. So here's what we do. What we're going to try and do is, well, let's begin to look at this. And you can't really understand this until you go through the process. But what we did in the first table is I took the x values, the original x values, and I kept them the same. And then I took the log of the y value. So you can see those numbers there. And if this data turns out to be linear, then it has the form y equals a times b to the x. And if, however, so I might try this first, right? And if this didn't work and this wasn't linear, then what I would do is take the log of both x and y and check and see if it was linear. Okay, so that's what you do. And if you've got a function that is exponential, it will come out linear with x and log y. If you've got a power function, if you graph log x and log y, it will be linear. So and the way to do this, by the way, folks, is you can just put formulas in to take the log of this this column over here, these cells over here, right? And if you need any help, I'll help you with that. But using spreadsheets and formulas in spreadsheets is a really important skill. Okay, so let's go down. I did do some scatter plotting. So there's the raw data scatter plot. Okay, so if you look, there's the raw data. I'll maybe make it a little bit larger. And you can see the raw data scatter plot clearly is nonlinear. It looks, it could be exponential, or it could be like a quadratic function or something like that, right? But we know for sure just by looking at a scatter plot. So that's the raw data right there. Then what we do is, oh, you can see here, now I've plotted x against log y. So there's the x values, and then on the y-axis, I have the log of y. And you can see there, I put what's called a trend line on it, a line of best fit, and you can see that it's perfectly linear. But the question is, how can you possibly get an equation from of a line that where the data is exponential? Well, we can. And now, what you do is, if you did this one first and you found it was linear, you wouldn't even do the log y and log x, right? You wouldn't even need to. And you can see that I did do the log x and log y, and I put a line of best fit through it, and you can see that it's definitely not linear because it doesn't go through all the points. Okay, oh, by the way, when you get into your table, one of the things that you can do is, it's called advanced edits, and under advanced edits, you go down, and eventually you're going to come to trend line. And trend line, you can pick linear, exponential, polynomial. We want to pick linear to see if the data is in fact linear. Okay, so Oh, and in this case, I could actually use the equation. I didn't notice that. So if I already had, that's interesting. That's very interesting. So I don't even have to do calculations on it. So there's the equation line, y equals 0.477x plus 1.669. Now I am going to show you a way to do that with calculations in a moment. So again, the big idea is you take your raw data, then you make a table of x versus log y, then you make a table of log x versus log y, and you see which of these is linear. Okay, so to show you how to do a calculation for slope or y-intercept in a cell in Google Sheets, here's what we do. So you put equal slope is the equation or the function that you use, and then you highlight the y data, put a comma, and then you highlight the x data. Hit enter, and there's the slope, 0.477. To do the y-intercept, you hit the equal sign, which denotes, which tells Google Sheets that you're going to enter in a formula, and you type in intercept, which gives you the y-intercept. And again, you do your x data, your y data first, and your x data after. Hit enter, and so there's the equation of our line, right? So let's take a look at the analysis. So I've got this equation of a line with a slope of 0.477 and a y-intercept of 1.699. Well, let's go over here and look at some things that we can do with that. And maybe what I'll do is just make this a little bit bigger in terms of font. Okay, so what you see here in the first line, ladies and gentlemen, is this is the actual equation that you created, right? Now, it's not y equals because on the y-axis, we didn't have y, we had the logarithm of y. And so I took the logarithm of the y value. So I've got logarithm of y equals 0.477x plus 1.699, but you don't want an equation that says log of y, you want an equation that says y equals. Well, what's the inverse of log? Well, it's raising everything to 10 to the exponent. So if you could do 10 to the exponent of log y, that's an inverse, right? That's an inverse composition. So it's just like the square root of x squared is x. No different if I take base 10 and I replace the exponent with log of y, well, that's just going to equal y. But I have to, if whatever I do to the left side of the equation, I have to do the right side. So what I'm going to do on the right side is I have base 10 now, like I'd make everything here be the exponent. So it's 10 to the exponent of 0.477x plus 1.699. And so then what I can do is separate those out because I'm adding here, which means I'm multiplying with the base. So I go 10 to the exponent 1.699 multiplied by 10 to the 0.477 all to the x, right? And we often did that when we were solving equations where we pulled things apart. So if you go in your calculator and you 10 to the 1.699, you're going to find that that's equal to 50. And then if you do 10 to the exponent 477, you're going to find that that equals 3. And look at that. Lo and behold, we get our actual original equation. Okay, so there's not a lot of work to that. However, there is some fairly significant understanding that can be acquired. And hopefully you'll get a sense of that as you work through this. So that's an example of linearizing data. And you have one data set which is going to be exponential like this, and you have another data set that's going to be like this. And there is a link on your handout to a math for biology students website where they go through an example of how to do this. So I've gone through this one with you. You're going to work through that example to do it yourself. Okay. I hope you may be hearing my or our two dogs in the background barking. My apologies if that's been a little bit disruptive. Hope you have a good day.